Right now, the James Webb Space Telescope has just finished examining two stars that astronomers have spent years suspecting are hiding something engineered around them, a Dyson sphere, the theoretical megastructure capable of capturing a star's entire energy output. If the answer inside that data had gone the other way, it would have been the single largest discovery in the history of our species. Two stars, both flagged years earlier as the strongest Dyson sphere candidates any systematic search had ever produced. For years, they sat on a shortlist, surviving test after test that should have eliminated them if they were anything ordinary. Every conventional explanation had already failed to explain them away. So this year, scientists finally turned the sharpest infrared eye humanity has ever built directly at both stars to settle the question for good. Here is what it found. I'm your John, and this is your channel. Subscribe now if you want more stories like this, because we are just getting started. Let's go back to the beginning. In 1960, physicist Freeman Dyson published a short, strange paper with a simple premise. If a civilization keeps growing its energy needs for long enough, eventually the only real estate large enough to satisfy it is the star itself. Not a planet, not a moon, the star. Build enough orbiting collectors around it, Dyson argued, and you could capture nearly all of its output rather than the sliver that happens to land on a nearby world. For over 60 years, this stayed almost entirely theoretical. A thought experiment passed between physicists and reused endlessly in fiction. But Dyson had also pointed out something that turned the idea from a fantasy into a testable hypothesis. A structure like that could not hide completely. The laws of thermodynamics do not bend for anyone, not even a civilization capable of dismantling planets for parts. Any machine that captures a star's energy has to get rid of the leftover heat somehow, and that heat has nowhere to go but back out into space, radiating in the infrared. A Dyson sphere, in other words, would not glow like a star. It would glow like a furnace with the lights off, a comparatively cool object radiating warmth it should not have. That single insight is what turned an idle thought experiment into an actual search strategy. If you wanted to find a Dyson sphere, you did not need to see it. You needed to find a star that was putting out far more infrared light than it should, with nothing else nearby that could explain it. For decades, nobody had the tools to run that search properly. Then, in the 2020s, that changed, and what the search actually turned up caught even the researchers off guard. In mid-2024, a research collaboration named Project Hephaistos published a result that quietly rattled the small, careful world of technosignature science. The team had built something nobody had attempted at this scale, a systematic infrared excess search across roughly 5 million stars, cross-referencing catalogs from the Gaia Space Telescope, the 2MASS survey, and the Wide Field Infrared Survey Explorer, or WISE, all within about 300 parsecs of Earth. Out of 5 million candidate stars, the vast majority behaved exactly as expected. But a small handful did not. 7 stars, all of them faint red dwarfs, showed a mid-infrared glow in the WISE data that had no obvious natural explanation. Their spectral energy distributions were consistent with blackbody temperatures somewhere between 100 and 300 Kelvin, precisely the temperature range predicted for a partial Dyson sphere, a structure that captures some, but not all, of a star's total output. This was not proof of anything. Everyone involved understood that. Red dwarfs can have dusty debris disks, background objects can contaminate a signal, instrument artifacts happen constantly. But out of 5 million stars, these 7 had cleared a bar that almost nothing else had cleared. And that was enough to justify years of follow-up work trying to rule out every mundane explanation before anyone even considered the extraordinary one. And so began one of the strangest elimination processes in modern astronomy. A hunt, not for evidence that these were alien megastructures, but for evidence that they were not. Here's where the story takes its first real turn, because ruling something out turns out to be almost as demanding as proving it true. Researchers began by hunting for radio counterparts, on the logic that if a background quasar or active galaxy happened to sit almost exactly behind one of these stars from Earth's point of view, it could easily mimic the infrared signature astronomers were looking for. Using high-resolution radio observatories, the team cross-matched all 7 candidates against archival radio surveys and found offset radio sources associated with 3 of them. Follow-up observations at multiple frequencies confirmed that at least one of those was a background active galactic nucleus, a supermassive black hole devouring material far beyond our galaxy, its light happening to line up almost perfectly with one of the 7 stars as seen from Earth. 3 candidates fell quickly, but 4 remained, and 2 of those 4 refused to fall at all. Designated simply Candidate D and Candidate E, they kept surviving every test thrown at them. No radio counterpart, no obvious optical contamination, nothing in the archival data that could explain away the excess. By the time astrophysicist Olivia Curtis and her colleagues at Pennsylvania State University picked up the analysis, Candidate D in particular had become something close to a best-case scenario. It had passed every archival diagnostic available before anyone even considered pointing the most expensive telescope in human history at it. As Curtis would later describe it, Candidate D had become the most promising Dyson sphere candidate on the board, the one real M-dwarf star, out of 5 million, that nobody had yet been able to explain away. That is the moment when a research proposal that had once sounded almost embarrassing to write down, request time on the James Webb Space Telescope to check for an alien megastructure, suddenly became one of the more serious Technosignature proposals in recent memory. Telescope time on Webb is one of the most contested resources in modern science. Proposals compete against cosmologists studying the earliest galaxies, planetary scientists mapping distant exoplanet atmospheres, and dozens of other high-priority programs, all fighting over a limited number of observing hours each cycle. For a Dyson sphere search to earn a slot, it could not simply claim the possibility was interesting. It had to demonstrate that every conventional explanation had already been exhausted, and that Webb was the only instrument capable of resolving what remained. Candidates D and E met that bar, specifically because nothing weaker could settle the question. Ground-based telescopes lacked the resolution. Older infrared missions lacked the sensitivity. Only an instrument capable of imaging in the mid-infrared with the sharpness of Webb's mid-infrared instrument had any real chance of separating a true anomaly from a coincidence of alignment. Now, let's talk about what happened next, because the tool that finally settled the question was not a bigger version of the same instrument that found the anomaly. It was something categorically better suited to the job. WISE, the survey telescope that flagged these candidates in the first place, is extraordinarily good at scanning the entire sky quickly. What it is not good at is resolving fine detail. Its images blur together anything close enough in the sky, which means a single bright pixel from WISE could just as easily be one object or several objects, stacked on top of each other from our vantage point. For a star sitting in a crowded patch of sky, that blur is not a minor technical footnote. It is the entire ballgame. The James Webb Space Telescope's mid-infrared instrument, by contrast, offers exactly the kind of sharp, high-resolution view that could finally separate a single glowing point into its true components, if there were multiple components to separate. In 2026, the team pointed Webb at both remaining candidates and began imaging them across a range of infrared filters, watching closely for the one detail that would answer everything. Was the infrared glow coming from the star itself, or from something else entirely, hidden in the same patch of sky? Within weeks, the results were unmistakable, and they did not come back the way anyone building a Dyson sphere search would have hoped. At the shortest infrared wavelengths, both candidates looked exactly like ordinary stars. But as the observations stepped out to longer wavelengths, 10 microns, then 15, something changed. The star's light began to fade, and right next to it, a second source began to brighten, until at the longest wavelengths it was the second source, not the star, doing almost all of the glowing. Once researchers saw two distinct sources where WISE had only ever recorded one, the explanation became obvious. The star was never the thing producing the excess heat. Something else, sitting almost perfectly behind it from Earth's point of view, was. Both hidden objects turned out to be galaxies, not stars, not structures, not anything remotely artificial. They were not random background clutter either. They were, in their own way, almost perfectly engineered to fool this exact kind of search. Behind Candidate D sat what astronomers call a hot, dust-obscured galaxy, nicknamed a hot dog, a galaxy whose central supermassive black hole is actively heating enormous surrounding clouds of dust to extreme temperatures. That process produces exactly the kind of strong, warm, mid-infrared glow that a partial Dyson sphere was predicted to give off. Behind Candidate E sat something different but equally deceptive, a dusty starburst galaxy, a system undergoing an extraordinary burst of new star formation, wrapped in enough dust to radiate powerfully in the infrared while staying almost invisible at shorter wavelengths. Neither explanation was exotic to astronomers. Hot dogs and starburst galaxies are both well-known, well-studied categories of object. What made this case remarkable was the coincidence of geometry. From Earth, each of these galaxies happened to sit close enough behind an ordinary red dwarf star that WISE's limited resolution blurred the two into what looked like a single anomalous source. In the case of Candidate D, the offset between the star and the background galaxy was measured at roughly 1 arc-second, an angular distance so small it has been compared to the apparent size of a coin viewed from 3 miles away. Candidate E was even more deceptive. Its background galaxy turned out to be an extended clumpy structure, and the foreground star happened to land almost exactly on top of one of its brightest infrared knots, making the two sources nearly impossible to separate without an instrument as sharp as Webb's. Think about what that actually means. Two of the strongest Technosignature candidates ever identified, survivors of years of increasingly aggressive testing, turned out to owe their entire signature to a geometric coincidence involving objects hundreds of millions or billions of light years farther away than the star itself. Not a flaw in the search, Not a mistake by the scientists. Just the universe being deep enough and crowded enough to occasionally line things up in a way built to deceive. Here is what deserves to sit at the center of the story, because the headline, "No Aliens Found," undersells what actually happened. This result did not close the search for Dyson spheres. It sharpened it. Before this study, the field lacked a clean, repeatable way to distinguish a genuine megastructure candidate from a background object impersonating one. Now it has exactly that. A demonstrated, tested method for peeling apart a suspicious infrared source into its true components, using high-resolution imaging and spectroscopy. Every future candidate that turns up in the next generation of surveys can now be run through the same diagnostic playbook that just cleared candidates D and E. That playbook is arriving at a useful moment. In 2026, a separate team out of the University of Arkansas published a 4-test checklist specifically designed for evaluating Dyson sphere candidates, timed to a rare convergence of capability. The James Webb Space Telescope, the Vera-C Rubin Observatory, and the Roman Space Telescope, all operational in the same window for the first time. No single one of these instruments can answer every question on its own. Webb specializes in exactly the kind of dust spectroscopy that unmasked candidates D and E Rubin is built to track how a source's brightness changes over time, watching for the kind of variability a natural object might show that an engineered one would not. Roman offers wide-field infrared characterization capable of comparing a candidate against enormous populations of ordinary stars to see whether it truly stands apart. Put together, for the first time in the history of this search, there is now a full toolkit capable of running a real Technosignature candidate through every major test it needs to survive, and candidates D and E were essentially the first real-world trial run. That convergence did not happen by accident. Rubin only recently began its full survey operations, methodically imaging the entire visible southern sky over and over, building exactly the kind of long baseline variability record that a one-time snapshot from Webb could never provide on its own. Roman is still ramping toward its primary science mission, but its wide-field infrared surveys are already being planned with searches like this one in mind, precisely because a target that looks anomalous in isolation often turns out to be unremarkable once measured against tens of thousands of similar stars. Individually, each of these 3 observatories closes off a different way a false positive can slip through. Together, they close off nearly all of them at once, which is exactly why the same research group that just cleared candidates D and E is already treating this case as the template for how every future candidate will be handled. We know that out of roughly 5 million stars scanned by Project Hephaistos, only 7 ever produced an infrared signature strange enough to warrant serious follow-up. We know that of those 7, radio observations quietly eliminated 3, revealing them as distant active galaxies rather than anything closer to home. We know that the remaining 2, candidates D and E, survived every archival test available for close to 2 years, making them, for a brief window, the most credible Dyson sphere candidates ever identified by a systematic survey. And we know that when the James Webb Space Telescope finally turned its sharp infrared eye toward them, both signatures dissolved into background galaxies, a hot dog behind one star and a dusty starburst system behind the other, each one an accident of cosmic alignment rather than evidence of anyone else out there. None of this was visible to WISE. None of this was resolvable by any instrument that existed before Webb. It took a space telescope sensitive enough and sharp enough to separate 2 overlapping infrared sources that had spent years successfully impersonating one. Every step of this elimination process came from researchers who were simply patient enough and rigorous enough to keep testing something the rest of the world might have been tempted to either dismiss immediately or believe uncritically. That same patience is about to be tested again. There is a real possibility that the next candidate to reach this stage of testing will not dissolve into a background galaxy. Project Hephaistos scanned roughly 5 million stars and found 7 worth a second look. The broader galaxy contains hundreds of billions of stars, and current and future infrared surveys are only expanding the fraction of them we can meaningfully scan. The method that just ruled out candidates D and E is not a dead end. It is a filter, and filters exist to let something through eventually, if there is anything real to find. What makes this story different from most Technosignature announcements is how undramatic the actual result was. No press conference, no declaration of first contact, just 2 research papers quietly walking back 2 promising candidates while handing the entire field a sharper set of tools than it had before. That is how most real scientific progress happens, not with a single explosive answer, but with each false positive making the next true positive. If one ever arrives, that much easier to trust. Somewhere in the next round of infrared surveys, among stars nobody has closely examined yet, there may be another candidate waiting to be flagged. And this time, the astronomers testing it will know exactly what questions to ask, exactly which instruments to point at it, and exactly how easily a distant galaxy can wear a star's disguise. Whether the next signal turns out to be another coincidence of geometry or something that finally survives every single test is a question nobody can answer yet. If this kind of story is what you come here for, subscribe right now and turn on notifications, because we are going deeper into the edges of what science actually knows next time. Drop a comment with what surprised you most in this video, and share this with someone who needs to hear it, because this story deserves more than the silence it is getting.